Welcome to the course on FPGA based signal processing systems. Continuing with the timing controls, we'll be looking at all the 6 combinations of procedural assignments. For example, blocking, non-blocking, sequential, concurrent execution, and delayed evaluation, and also the delayed assignment. In the hardware perspective, that because we'll be doing all the Verilog code, synthesize it, and then dump into the FPGA. So in this process, we need to find the equivalent hardware components for the code. So in this, one of the hardware components which is very much useful in the case of transition propagation methods, in which there are two kinds of delays are modeled. Suppose the buffer, if you have a buffer which has some propagation delay, then the input to output transition. So how when the buffer has a propagation delay, how this input is getting transferred to output, how do we model that in the using the delay methods. So the initial delay, there are two types of hardware delay models, like one is initial delay and the other one is this transport delay, where initial delay has the finite switching speed. So if you sample it at the signal at a finite instance of time, whereas in the transport delay you have this infinite switching, that is very closely you sample this signal. So near infinite, ideally every sample time, every instant is the signal is sampled. So the near infinite switching speed, or it is a finite switching speed, that depends on that. This delay models are initial delay and transport delay. What is the equivalent Verilog code for it? What is the model we are talking about? So in this finite switching method, so if you're sampling at one instant, and then after a 5 nanoseconds of delay, you are again sampling this data, in the sense in between the data might have changed, so that glitches won't be propagated to the output in case of initial delay modeling. So if the glitches needs to be avoided, we can go for this Verilog code with the initial delay model. If you sample it at every instance of time, then that is infinite switching. That means whatever the changes in input will be reflected at the output. So that is the glitches even would propagate to the output. So these are the two delay models, in which one initial delay model, if we take out this, we can consider it as a buffer which has 10 nanoseconds of propagation delay. So these are in nanoseconds, 10, 20, 30, 40, 50, 60, like that. And at even you can see the signal which comes into the buffer is at 20. Before 20 it is 0, after that it becomes 1 for a while, and then it comes back to 0. At 30 again it becomes 1, and then it stays over there. Then at 45 it comes to 0. So this signal is given to the buffer which has 10 nanoseconds. As obviously what it should do, that every sample point, every point should be just delayed for 10 nanoseconds. That is what is expected. If we model this as an initial delay, in which that the 0, 20, they suppose 20 is becoming 1 here, okay. So that should be up to 20, it is reflected here, whereas the change that occurred in between 20 and 30, you can consider this as a glitch. So that change would not be reflected over here. So the 30 point is directly coming as 40. See, other things from about up to 10, 20, this is modeled up here as 30. So at point of 20 is that 30, but the change is not reflected in this case. So because of the duration, the glitch which goes in comes out, and then it falls away. So that this is the thing which is avoided in the initial delay. You can see only the duration of the signal which stays more than this 10 nanoseconds are captured. So if it is below 10 nanoseconds, that would not be reflected at the output. So this is the case of initial delay with the finite switching. You look at here and then here and here, 40, 50 and so on, but in between that whatever happens will not be reflected. Whereas the transport delay model, which is infinite switching, every instant of that, even the glitches would propagate to the output. The same thing which we consider here, so 0, 10. So you can see that 20 is just at 30 because of 10 nanoseconds propagation delay, and whatever the changes are here again. So it is infinitely switched or sampled every instant. So this at 25 whatever the change also reflected at 35, and then 30 to 40, and then 40 to 50, and 45 to 55, and so on. So this is another delay model, which is the transport delay. So both are useful depending on this applications that were, in this case, you want to have this every instant of time to be captured at the output, even with the 10 nanoseconds of propagation delay. So it is beneficial to have this model as well. So the hardware can look at these delay models in two different ways. One is initial and the transport delay. So how this is coded in this Verilog? Let's see that procedural assignments generally we take a few examples that for the combinational logic, and then we'll look at the sequential logic as well, the concurrent assignments, the combinations which I told in the beginnings. We'll look at one by one now. So this module has the module name timing input in output reg, which has, there are multiple outputs, we're getting different outputs in the same code. So this always at in, this is a behavioral code, input is assigned to output, that is, this is a blocking assignment. Okay, so there is no delay in it. Okay, so the next one similarly, always at the input, whatever the input is 1 bit, here output is also 1 bit. So this is changing this blocking to non-blocking. Input is assigning the value to O2, where through this non-blocking assignment, there is no delay over here. Always at the end, the third category is this in, as it is #5 O3 equal to n. So this is blocking 1, again it is a delayed evaluation. So whereas the next one is the non-blocking and the delayed evaluation. So the same thing with the non-blocking and delayed evaluation. So, the fifth one is blocking and the delayed assignment. So you can see the combinations of, we are taking blocking, no delay, non-blocking, no delay, blocking, delayed evaluation, non-blocking, delayed evaluation, blocking, delayed assignment, and this next one we are going to look at is this non-blocking delayed assignment. So how this what would be the O1 for a given input? Okay. So in this case, we have the test bench. So we had this input wires or the outputs in the different always blocks, and then instantiate them in this 1, O2, O3, O4, O5, and O6. Instantiate it and give the stimulus. Input is initially 0, and then input is changed to 1 after 10 time units. After that, it made 0. After that, 1. After that, it becomes again after 3 time units 0, 1, and so on. This way, the stimulus is changed, the input, and this is monitored using the test bench at $60 finish. So we would look at this statements one by one and then see what is the output we are getting over here. So this is the output. I would like to explain it with the you can see the TCL console, which gives the input and then output, all the outputs over here. So we take for this discussion here, this is always at the end, the first statement where is input is assigned to output. So the input which is given in the test bench listed here, the input which is going to 1 at 10 nanosecond, and then another 10 nanosecond it becomes over here, and then 20 it becomes 0. After 10 again it is becoming 1, and then after this 33 it is becoming 0 again. At 36 it is becoming 1 that, and after that at 9 after 9 in the sense just 36 plus 9 here 45 it becomes 0. So this is the input which is generated for the code or given to this code. So how does this always blocks giving the output? See that output in this case, yeah, output 1. So whenever there is a change always at the rate in, that means it senses the sensitivity list contained only the input. So whenever there is a change in then it gets into the statement which is over here. Similarly, in all other cases, it is whenever there is a change in, it gets into the statement to execute the next statement. So wherever in here you see in the first case in is assigned to output. So there is no delay, nothing, immediate assignment, so it assigns it. So whatever that input change, so you can first change occur, it is 0 everywhere, okay, and then the first change occurred at O1 at 10, so it is assigning that immediately. At 20 it is becoming 0, 30 it is over here, 33, 36 and 45. So there is no delay. The first this is O1, okay, this case. And second O2, there is, it is non-blocking, still there is no delay, and there is no other non-blocking statement in this case. Even if it is the case, then that all this non-blocking will be executed and assigned at this current time step, what are the non-blocking statements are there, and then at the end of the current time step these outputs would get the whatever the input value was. So here this is only one statement. So O2, it is also getting this in at the current time step, that is 10 here. This is O2. Similar, this output 1 and then it goes to 0, 30 again it is 33, there is 0, 36 it goes up, and at 45 there is no delay, 0 delay. So this is of O1 and O2. So fine, then and come to the third case, it is #5 O3 in. So this O3, that what happens here, input, whenever there is a change, yes, it tries to execute it, but it is not the time 0 there with these, where at #5 we have this input should be evaluated and assigned. So what it does is, you can see the O3, that is here up to 5 there is no output here, okay, it is, there is no evaluation or assignment in this case, okay. So after this 5, this the 10 change is reflected at 15, you can see over here, this is 15, okay. So because of the delayed evaluation, and then this change would be reflected here. So what happened to the 30 change, which is not reflected, okay. So this is evaluated before assigning, that means it is having after 5 10 time units. So this signal changes, so it maintains that 0 only at this point, okay. So there is no this glitch, which is the duration of below the propagation delay, what we have considered as an initial delay, okay. So this change would not be reflected if you have this immediate assignment with the delayed evaluation #5. This is regular time delay, and this 36, that is at 36 point, even there is a signal change, that is reflected at 41. You can see that this is I could even say this, these are from the I would be using it if it was this input, because that is same as that we have marked here. So this input edge, and this is not over here assigned because of this the change which is occurring before that. And then at 36 it is, the change is reflected in 41. At 45 whatever was there, it is reflected at this is 45 plus 5, that is 50. This is becoming 0. So O3, which is just a 5 time units delay of the inputs, and at the same time did notice that this glitches won't be transferred to the output, okay. So this is the example of this initial delay. So this delay evaluation itself is delayed here. So similar case of the #5 O4 less than or equal to in this non-blocking, if the same statement with non-blocking, we can see this O4, this is O3 and O4, it behaves similarly, that is in this same case of this case is, this is transferred here 5, because there is no other statement in this block as sequential, or so this would also be neglecting this assignments, okay, at 5, and the one which is over here also the initial one. So that's also a shift of 5 time units in the output. But initial delay, which preferable one is with the blocking statement instead of having the non-blocking statement. Suppose if there is anything near the non-blocking statements, this would cause even you won't be expecting the same output here. So, preferable for the initial delay is that blocking statement. And the case always at the in the next O5, here you can see this, it is not after. So, these are intra assignment delays, these are regular delays, and then the one which you have is intra assignment delay with blocking and non blocking. So, that makes a difference. Whenever there is a change in input, it gets evaluated, but that change is not reflected immediately, it is delayed 5 time units. Okay. So, the difference between this is that this is evaluated at time t equal to 0, this is getting evaluated only after 5 time units. Okay. So, this is evaluated whatever this time, and it is assigned after 5 time units. So, the change is there, it is getting assigned over here, and this change similarly is getting assigned over here. Also, this change you can see it is assigned over here 5 times, it is evaluated and stored. We can say that this is having the temporary register. If you recall in the previous lecture, that stored value is getting reflected over here, whereas these cases doesn't. Okay. It doesn't have this particular one initial delay, and this initial delay of these cases did not reflect these change at these outputs, whereas the intra assignment delay, yes, it gets reflecting, but it looks at the next change of this, that 33. But if you look at the 33 and the before assigning it, that is this 33, the 30 which is reflected before assigning this 33 as the change, so it is not reflected in this case. So, it maintains that same at whatever is at 30. So, next 40 it is looking at this change is not reflected. So, that 40 whatever the change is reflected at the 45. So, this is reflected over here to 0. So, this is a case of neither at 0 delay nor or initial delay or even the transport delay, where it all of this 30 this glitches are the duration of the change which is less than the delay which is specified here is reflected. So, this model, this is intra assignment delay, but immediate assignment. And then the last one which we have is always at in, we have this O6 less than or equal to #5n. In this case, this is also an intra assignment delay and with non blocking assignments. So, when you use the non blocking, what happens, this is change, just when there is a change, it is trying to execute this statement and the in is evaluated. So, you can see that it is assigned after 5 time units, also the same way here, and this change, there is no change over here, and this change is also reflected as in the case of intra assignment delay. And even though if there is a change before this assignment, okay, that would also be considered in the case of non blocking, that old values is also preserved. So, you can see the reflection of this 33 as well as 36 at the output, 45 even has the delay. So, this is the transport delay which reflects every change in the input. That is what the infinite switching case of the model, that in transport delay. So, if you want to model the initial and transport delay, which is this intra assignment delay with non blocking, for the initial delay to avoid it, this would be the preferable one, that is the delayed evaluation with a blocking assignment. So, I think it clarifies that were different cases of blocking and the non blocking with the delay, regular and the intra assignment delays. Coming to the sequential logic procedural assignments, whereas what we had seen is this even we use the always block, but the assignments which is using the kind of buffers which is just assigning the inputs to the outputs with and without delay. So, the sequential logic assignments without any delay. So, we will consider this code with the module timing 1, input clock, output y1 and y2. So, always at the rate of passage of the clock, again input is assigned to y1 and y1 is assigned to y2. And if you recall that this example we did in one of the lectures, so it's very well in the shift registers. If input is getting whatever at the passage of the clock, this input is sampled, whatever the input, it's assigned to y1 because it's an immediate assignment, and the same y1 is assigned to y2. So the hardware structure or the what is formed over here is that input, you have the flip-flop D and the clock for the two flip-flops are same. So input is assigned to y1, the same output, and the same y1 is getting to y2, meaning that because input is immediately get assigned to y1, so the input is going to the other flip-flop, and y2 also getting the same at the same passage of the clock. So this model is tested over this test bench y1, y2 and the inputs clock and in. Timing 1, instantiate this one. Clock is generated as usual in any of the test bench, because we use this clock as a passage of the clock for assignment. So in this case, you have initialize this signal. Next, the test bench 1 is assigned to in after 5. After 15, the input is changed to 0. Then after 20, again this is the test cases we had given. After 18, made it 1, and after 7 again made it 0. End, and monitor these outputs, display under the monitor. So $finish after 65 time units, that is after all this calculation of this, it is not at 65 after this. So the N, so this is a test bench which we had used for getting the output. So the parallel flip-flops, what we had, two flip-flops which is getting the same input. So the inputs I have listed over here, and the clock you can see in this case. So what is the input is assigned to y1. So the input first input it is changing at 5, okay, here. After that it is made at 15, it is made, so 5 plus 15 it is 20, at 20 it is going to be 0, and then after 20 nanoseconds, that is 40, it becomes 1, and after that it is becoming 40 plus 18, 58, it will be again 1, that is, so it is maintaining here. After that, after here 7 of this 58, then it goes to 0, which is not shown over here. So the y1, if you look at this, at passage of the clock, what is the input, because there is no delay and it is assigned to y1. At the same time, the y1 is assigned to y2 as well. You can see that because of the immediate assignment. At passage of the clock, the input is assigned to y1 and the same is assigned to y2 as well. At the passage of the clock, here input, this is assigned to both cases. So it is forming a parallel flip-flop in case of the sequential the always blocks. Here we have with blocking assignments with no delays. So if you consider this block again, if we have the sequential logic again, this assignment with no delay, but if you change that the code with the y1 less than or equal to n as a non-blocking, that means in the input what we had need to be assigned at y1, input is evaluated at passage of the clock, y1 is also evaluated at the passage of the clock. After that, this to y1 and y2 gets the output. So in that case, this y1 is not the one that is updated, but this y1 is which is going to be the old value which is getting assigned to y2. So now if we look at the equivalent hardware of this code, is that input which is getting into the D flip-flop and that y1 is again getting into the y2, that would y1 will be passing to y2, the change will be in the next clock edge. So it's forming a shift registers, okay. So the example, the clock we can see, though there is no delay, the input change here over at the clock edge, it samples the input and assigns over hit, samples the input and then assign over a hit, here, and then similarly at the third clock edge as well. Whereas y2 is, what is the y2 getting at the clock edge? This is not the same. This particular case is shifted to next clock edge. That means this point, what was there with the old y1, which is maintained here at y2. So it is not, since that first clock edge y1 has not getting any value. So y2 is shown over red, that is not even getting any value. So the first value what it gets, the y1 will be available to y2 at next clock edge. So this point will be available again at the next clock edge to y2. So there is, it's a shifting, that it's a shift register is formed using this code, and there is no delay. So this is the input change, and you can see the clock change and y1 and y2. So you can see the shifts in the outputs as well. So there is no issue if there is, this is sequential assignments, and then blocking and non-blocking. So if we have this same sequential logic thing, sequential assignments with delayed assignment. So taking the example with just changing them, that immediate assignment with #5. So here it is also with #5. So this is an intra assignment delay. So if we have this intra assignment delay, so the input is plus at passage of the clock, it is evaluated and assigned after 5 time units, and then y1 would it get the same value, or y2 as this. Okay. So here the model of this can be said like this. So that at passage of the clock, yes, input is evaluated, and after 5 time units it is assigned. So it is like a similar to the first case, that is after this, but with the delay of #5. So #5 you get what is at the clock edge, passage of the clock input will be passed to y1 after 5 time units. But that y2, okay, so this y1 after assignment, this y1 is sampled and take another 5 time units to assign it to y2. So that's what y1, and after 5 time units and look to y2. Or we can look at this as the clock itself is delayed for 5 more time units. That means the clock which is delayed clock of 5, and then at delayed clock of 5, y1 is sampled and assigned to y2. So this forms the delay case, forming a shift registers, whereas the shift register has 5 time units, as well as the second stage is also having the #5, meaning it is getting the delayed clock instead of the clock in this. So let's see the output over here. So the clock is shown here, the delay, and the input is sampled and assigned after 5 time units. That's what here. So y1 at this input, and that is sampled after 5 time units, y1 is getting the values, and again here this is taking another 5 time units. So this is y1, it is clear after 5 time units because of the intra assignment delay. And after this assignment, okay, so after the assignment, so the y1 is available now. So when this y2 will be getting the out, because y2 also has the delay, intra assignment delay. So y1 is after 5 time units, y2 will be getting the values. What is the y1 was? Y1 will be assigned to y2 after 5 time units. Or we can look at this as a clock which is having 5 time units delayed clock. That means here this delayed clock, and you can take this as a delayed clock side. So now look at this clock edge. Look at this clock edge. This is a delayed clock. So this delayed clock, which, and look at y1 at this delayed clock, and I take 5 time units and assign it here. Look at this y1 at this clock and then assign it. Look at this at the delayed clock and assign it. So this is of the second stage takes the when you have the delay in the sequential assignments and sequential execution and the blocking assignment. So, the first delay, and that is forming the second delay also, and the clock, you can notice the important one, the second delay is considered to be that y1 is sampled at the delayed clock or the two registers which is having the one at the delayed here. So, the assignment is 5 units delayed, in the sense the clock it should be looking at the clock which is the clock for delayed clock. Okay. So, this is the case of sequential with the delayed assignment, it's intra assignment delay, of course the delayed assignment, but the blocking with the blocking assignments. Whereas, if you say the delay, you see the delayed assignments in the same case with the non-blocking statements. So, the non-blocking, of course, this 5 time units are always there, but this value which is y1 will be updated here, or the value, because this old value will be updated in y2. So, this model is simply the input here and delay 5 time units, that gets y1. After that, y1 is delayed 5 time units, getting y2. Okay. So, this is the model of the non-blocking assignments with sequential execution. So, look at these the difference between that blocking and non-blocking in the sequential. So, the clock edge, passage of the clock, the input change is sensed and then it is assigned after 5 time units y1. So, similarly at this clock edge, say have 0 and it is reflected here, at this clock edge 1 and it is reflected at 1. Now, this y1 is as usual in the previous case, but y1 is not the immediate y1, that is the old y1 which is getting reflected here, you can see at the next clock edge. Okay. So, after 5 time units, you can see. So, over here and this is over here, the old values, because at the passage of the clock, if you look at it, this y1, so this would be again the 1. Okay. So, this 1, the old value is getting reflected in all these things. So, y1, so it is getting the y1 and y2. So, shift is simply the shift registers with delay. There is no second stage clock which can be observed in this portion. Whereas, the delayed evaluation, if we take the same code with delayed evaluation, so the hash 5, now it is switched to the first place, hash 5 y1 is equal to n, hash 5 y2 equal to y1. So, the evaluation itself is delayed. Okay. So, this forms the clock. So, it just forms a shift register with this hash 5 is at the first clock. It is because it is immediate assignment. So, the at passage of the clock, after 5 the input is sampled and the input is sampled and assigned, or we can say the clock itself is delayed 5 time units, checking input and assigning it. After 5, and even this clock is again 5 time units delayed, the clock, the passage of the clock, and check the y1 and assign it to y2. So, the evaluation itself is delayed. That can be modeled as this, the clock which is coming to the flip flop is 5 units delayed and the 5 time units delayed over here. So, let us look at this. This is the clock, and if we look at the first one, the clock is delayed for 5 time units. So, in the sense the 5 time units delayed clock, we can have it here. That is one thing, 5 time units delayed clock, and then another 5 time units. So, another 5 time units delayed clock will be at these edges, that is at the negative edge, the next 5 time units delayed clock will be. Okay. So, the next 5 time units delayed will be here, over here, and then this would be again here have the 5 time units, it would become this, and then next 5 time units here, this would go down and come up at this stage. So this is the third clock, which can be even you can say with so the third clock can be this, that is 10 time units delayed. So the second one is over here, so which is this timed clock. Okay, so this one. So now the first input, look at this clock and input, assign it, look at this at this point and then assign it, and then look at this point, this is 1, assign it to y1. That's all. So the second flip flop here, look at this clock which is over here and look at y1 and assign it. Okay, and similarly look at y1 and assign this over here, look at y1 and assign it. Okay, so this is with the case of immediate assignment, delayed evaluation. So the assigned value, the sampling itself is getting delayed for the input, because the clock edge, we could assume that this is the clock which is getting delayed for 5 time units and then 5 time units. Similarly, the case of delayed evaluation with non-blocking also exhibits the similar kind of assignments. So clock itself is getting delayed for 5 time units. So the same output which is having here 0 and which is D1, that is this is 0th, not this clock, this is 0 clock. So this won't be here, and the clock is looking at here, the first clock, look at here and assign it. Similarly, look at this point and assign it, look at this point and in 1 and assign this, whereas this is getting that after 10 time units, look at this and assign it, look at this and assign it, look at this one and assign this. So this is a shift registers with delayed clocks. With delayed evaluation means that delayed the clock. So coming to the current concurrent assignments, so we have the two always block in the same code. So there's always that passage of the clock. This is with no delay. Input is assigned to y1 and y1 is assigned to y2. Here, because of the immediate assignment, always we can have the indeterminate results. That is, input is assigned to y1, yes, and if it is updated, that y1 should be getting this output y2, or that's if y1 is getting our input y2, that will form a parallel flip flop, but that is not the case. So this can lead to the y1 is getting assigned or not. Okay, so this would take the immediate y1 value which is updated or not. That is an indeterminate result. Would be if it is assigned, it will form a parallel flip flop. If it is not, then that is going to be a question mark, that which there will be indeterminate result in this. So whereas in the simulator, which it is showing that it is going to be then, because of this immediate assignment, at passage of the clock this is assigned, and that y1 is immediately assigned in the but in the hardware it is not, so it would give the results which is indeterminate as well. So with y1 and y2 getting the same output, because this in that case it is not the model of this. After y1 will be y2 will be getting, this will be a parallel flip flop. So over here assign it, over here, and then this will also getting the same output. This will have the race condition anyway, because the y1 one is that the clock is race condition can be due to this sampling, and at the sampling edge you can have the setup time, hold time violation, also the data should not change at the passage of the clock. That would also cause the risk conditions in these types. So again the concurrent statement with no delays of non-blocking. So non-blocking is clear here. Again the input is sampled and the clock y1 is sampled. That y1 will be the old value. So there is no this will take at the current step end, y1 will be getting the value. Before that this is getting sample. So there won't be any issue in the concurrent assignment of non-blocking. So it's preferable to have when the concurrent assignment it is the non-blocking assignment. So input and then y1 is getting that value. After that it is passed to y2. Let's see that here. So our passage of the clock input is getting over here, and this is over here and here, and this is also this y1, the next clock edge only will get this output transferred to here y1. Okay, so because it is taking at this clock edge, it takes the old value of y1, that is y2 take the old value of y1. So it's not getting assigned till that point. This again forms a zero delay shift registers. Whereas coming to the delayed evaluation of these concurrent assignments. So #5 you can see the concurrent assignments, passage of the clock and passage of the clock. Again this would the immediate assignments, whether it is delayed or no delay, it would cause the same kind of this condition here. If this is evaluated and assigned at 5, then that assigned value is taken, yes, it's okay. Otherwise this would form a race condition in that case. So this #5 forms, as we have seen in the previous cases also, that would be the clock is delayed 5 time units, and this is also getting the clock which is 5 time units of the clock which is there, 5 time units delayed and 5 time units delayed. So but this immediate assignments doesn't form the series flip-flops, it would have the parallel flip-flop in that case. So here the clock edges, but this is not looking at this clock edge, but it would look at the clock which is delayed clock. So at the delayed clock, it is sampled and assigned, and here also it is assigned in the simulator. It gives that parallel condition. So this would definitely an indeterminate result in the hardware. So it forms the race condition in this case, where it won't be because of the immediate assignments. That would create a confusion in this case in the realization. So noting down that delayed evaluation can be looked at as a delayed clocks. So the concurrent assignment with the non-blocking and delayed evaluation. So this is the passage of the clocks. We have the same with the non-blocking statement. So in this case again the clock is delayed because of the evaluation is delayed, the 5 time units, and this is also 5 time units delayed clock, but because of the non-blocking assignment, the value is determinant which is stored, and then this would be sampling the previous value at the same time. Okay, so because of the non-blocking condition, so it forms the shift register. So here the clock delay which can be taken over this point, you can see this is sampled and assigned, this is sampled, assigned, and this is assigned over here, whereas the y2 is getting the value of y1 later. Okay, so not because of the non-blocking assignment. So this race condition can occur only when there is a data change at the clock edge. Okay, so it doesn't here, if there is a data change, then there is a possibility of that. It can occur in anywhere that data should not change at the clock edge. That we would be discussing separately with the setup time and hold time violation during the timing analysis. So otherwise this has this delayed evaluation of non-blocking is fine. That doesn't cause any problem. So the concurrent assignments with the intra-assignment delays. So intra-assignment delay with blocking and non-blocking. So in case this at the passage of the clock, yes, it is checked input is evaluated and assigned later after 5 time units. So it is not a delay of clock, it is the delay of the data. Okay, so input is assigned after 5 time units to y1, and then y1 it is assigned to y2. So in this case you can see the inputs is the input is assigned after 5 time units. This is assigned after 5 time units. Here it is assigned after 5 time units, and then old value of this y1, this is having y1 which is transferred to here, and y to y2. So it's just a shift register with delays, intra assignment delay. So only the glitches would be passed or not. That is the only case which has the which it has the problem. If there is a closer glitches, this case would not pass. So in the concurrent assignment, we have the non-blocking, that it would this would also be forming the similar thing, because it would closely watch the input change here. The clause as we have seen in the intra-assignment delay with non-blocking assignment, whatever the it's equivalent to the transport delay if you use it as a one always block. So it's a shift register with sampled and assigned, and this was getting old value and assigned. So there is no this is sampled here, assigned, and that is going here. At this point it is sampled and assigned, that value will be here, sampled and assigned, that will be after 5 time units. So this is the shift register with the delays. So only that to be noted, the clock, wherever this clock itself is delayed, the delayed evaluation causes the clock to delay. Okay. Otherwise, this would be when there is an immediate assignment, would form a parallel flip flops. Otherwise, or if it is a non-blocking assignment, that would form a shift register of the flip flops. So to just to conclude, if there is no delay, use blocking assignments. That is very simple. To use if for the initial delay to be mimicked in the behavior, then use the delayed evaluation with blocking assignment. For the transport delay, yes, it is non-blocking with the intra-assignment delay. That's the key for the combinational logic. Whereas for the sequential logic, no delay, use this non-blocking assignments. That is good. To old value will be updated and so on. So with delays, use this intra-assignment q less than or equal to #5 or whatever the delay to d. So the intra-assignment delay is preferable for the sequential logic with delayed assignments, and then this is with non-blocking assignment for the no delay case. Thank you.